Well, Assalamu alaikum, dear students. I am Engineer Abdul Basit, and we are in week number 11, okay, and lecture number 21 of subject Geotechnical Engineering 1. And the topic that I'm going to discuss today is soil structures. Okay, so straight away coming to the topic, what does it mean by soil structures? Simple, we can say that the arrangement of the particles in a soil sample is called soil structures. Okay, so what does it mean by arrangement, and what are the parameters that are governing this arrangement of the particles? So we have different parameters, like for example, the size of the particle, the shape of the particle, and then the ingredients, the extra materials that are present, and the type of the minerals that are present in the soil sample. And now the availability of water also affect the arrangement of the particle, and then salts and different flocculants and all types of these materials may also affect the arrangement of particle. So simple, we can say the soil structure is that type of engineering property which may affect the rest of the engineering properties, like the shear strength, like the compressive the bearing capacity of the soil, and different other types of the properties are engineering properties that we may need in the design of foundation and investigation of soil for our engineering purposes. Okay, so this is like a type of a simple picture I am displaying here, in which we have different types of the soil structures. But coming to the microscopic structure of the soil, so here it is. There are already I have discussed these things, but coming to this picture, first of all, in this figure you can see that we have solid particles, okay, and these solid particles may be of clay particles, maybe grains, maybe silt, maybe sand, and maybe the combine some type of material. Okay, now you can see there are a lot of you can say a greater size voids available over here. So you can see that this A figure shows the loose soil and this one shows the dense soil. Okay, in the dense soil you can see the size of the void is comparatively small as compared to this A figure, where the loose soil has the void size a bit greater than as compared to this one. Okay, so simply we can say that in loose soil the engineering properties will be different and as compared to dense soil, and they will have different structures as well. Okay ji. So then we have the different types of soils available, like cohesive soil and cohesionless soil. Okay, so then cohesive soil and cohesionless soil will also have different types of structures available. So let me go through it. First of all, coming to the cohesionless soil, as the name indicate that it will have no cohesion. So I expect that you will know what is cohesion, but let me go through it also. What is cohesion? First of all, cohesion is the the force of attraction between the molecules of the same substance, or that same type of molecules. Okay, like for example we have water, so the attraction between the water molecules, or the attraction of the water molecule with each other, is called the cohesion. Okay, when we pour this water in a glass, okay, so what will happen? There will be two types of forces. Then one type of force will be between the molecules of water, and that is called cohesion, because it's same molecules and same substance. But the other type of force may develop with the between the molecules of water and the wall of the glass. Okay, so let me show it practically. For example, this is that glass. So then the molecule of water that is poured inside this will have some attraction with this wall of the glass. Okay, so that type of force is then called adhesion. Okay, so no need to explain it further. Then coming to that different types of cohesionless soil. Okay, so it is obvious that it will have no cohesion. Then we have two types of cohesionless soil. Then that is single grain soil and honeycombed. Okay, so what will be the arrangement of the particle in single grain soil and then in the honeycombed, and how to find out these voids are the compaction of you can say the void ratio of these types of structure. Okay, so coming to single grain first, here you can see this is that arrangement for single grain soil, where all the grains may have like same size, and it is like an ideal type of situation where you can see that all the grains are having same size, and the openings or the voids between these particles is also of the same type, and also you can see that the arrangement is in a very regular manner. Okay, so then we can have two types of single grain soil. One is that this loose soil, and then we have this compacted soil. So how to determine this? uh, let us consider this picture first. Okay, uh, you can see it here that this is one particle, second particle, and many particles are here, and you can also see the voids in between these particles. Okay, so let me plot it for you. uh, Here it is. This is the particle, and now in this circle you can see this is the void. Okay ji. Now for example, the the particle that it is present here is in the form of, or in the shape of a sphere. It's a complete particle, it's a sphere. Okay, so then it will have some diameter, like for example this is the diameter of the sphere. Okay, so how to develop this formula now, this one? Okay, uh, how to do it? Simple. What is void ratio equal to? Void ratio is equal to volume of the voids to divided by volume of soil solids. Okay, now is equal to how can we define this volume of voids now? Simple. From the total volume you will subtract the volume of the solids. Okay, and then divided by volume of solids. So this can be the formula. Okay, so the total volume, let's say I am considering this one cube that is being plotted here in the in blue color. Okay, I'm considering this one cube, but here from one direction or in a single plane you can see it that it is a rectangle, but this is not a rectangle, this is a complete cube. Okay, this do have a height out of the plane as well. Okay, so what will be the volume of this cube? That will be the total volume. Now then subtracting the volume of this sphere. So what is the volume of the sphere? That is denoted by the Vs. Okay, and the volume of the cube is denoted by d cube. Why it is so? Because it is a complete cube. Okay, and cube will have a volume equal to length multiplied by height multiplied by width. Okay, so if all the length, width and height are equal to d, so then d multiplied by d multiplied by d will be equal to d3. Okay, volume of sphere. Volume of sphere actually refers to the volume of solid part. Okay, how it is? Because you can see this is a particle, so the volume of the particle is that solid part of the soil sample. Okay, so you can also say that Vs refers to volume of sphere or volume of solids. Both of them are the same. Okay, now putting these values in this equation. Okay, how can we do it? Total volume is equal to d cube. Okay, so then this is the d cube instead of this v, total volume. Now put this pi d cube divided by 6 instead of the volume of soil solids or volume of the sphere. So volume of the sphere is can be determined by this formula. Okay, for a diameter d. Okay, so this is the formula for the volume of the sphere. Okay, pi d cube divided by 6. Similarly, divided by total volume of soil solids, or you can say volume of the sphere. Okay, as both of them are the same. So the void ratio from this formula can be determined as all the values here are given. So then you can find it out that for loose soil we have the word ratio 0.91, which is quite a greater value. It's a higher value, okay, or it cannot be neglected, okay. But in the dense soil you can see this will be the situation, and in this case you will see that the cube cannot be drawn against one particle because it is like difficult to draw it or mention the boundaries, okay. Then we will draw in the form of, in case of dense soils, the formula will be, or you can say the cube will be plotted in this manner. You can see this one. Let me plot it. I'll try to plot it straight, but I can't. This is that volume now, okay, this cube now, okay. So you can see that, let me remove it first to make it a bit clear to you people. This is that volume, okay. And now you can see what is the diameter of this cube, or you can say the diagonal of this cube. So this refers to two spheres, okay. So two spheres mean two diameters, so this will be 2d, okay. You can calculate it by looking to it, observing it closely, then you will find it out that it is 2d, okay. Now if this one diagonal is 2d, so what will be the height of this triangle, this base or this height of the triangle? So that will be equal to d under the root 2. You can simply find it out by Pythagoras theorem, okay. So then how to put these values over here? So the cube will be like, this is the height of the cube, this is also the width of the cube, and this is also the length of the cube, okay. So d under the root 2 multiplied by d under the root 2 multiplied by d under the root 2. So this will be the total volume, okay. So here you will put this value multiplied by, or you can say power 3, okay. Then instead of this value pi d cube divided by 6, what will you put here? This area total 2d, okay. 2d is the like the area of the sphere that is inside this. So we have two spheres, one sphere, half sphere, half sphere, half sphere, half sphere. So we will have two spheres over here. So you will subtract that two spheres volume from this, okay. So you will multiply this value with the 2, okay, and similarly here this will be also multiplied with 2, this thing, okay. So you will get a new formula and a new value for void ratio in case of dense soil, okay, and that value will be 0.35. here it is, okay. So when it is closely densely packed material, the void ratio will be 0.35 for single grain soil, okay. And for loose soil, you will get the void ratio equal to 0.91. How to calculate it? I already told you. This is the way to do it, okay. Now this type of arrangement is called simple cubical packing, or this arrangement is called cubical shape, okay. So this is an ideal type of situation. You can consider it for these evaluation of the formula and the void ratio, okay. Now honeycomb structures. So this is that shape for the honeycomb structures, okay, honeycomb structure of the soil. So these are small circles of the solid particles, and in between you will see that this is that void space, this is that space of the voids, and this is voids and the voids, okay. So all the particles will be arranged in the form of circles, and the total voids will be combined to make it a larger size of the voids, okay. So this is called honeycomb structure, and there is no any equation for this to calculate it, okay. Coming to the cohesion soil. So cohesive soil refers to that type of soil where the particle of the soil are having some attraction with each other, and they are being attracted to each other, okay. So while talking about the soils, already I told you that clay particles have negative charge on this, or on their surface, like you can see in this figure, okay. This is this sheet, or you can say this whole crust is actually of having negative charge on its surface, okay. So when the water molecule are coming close to this clay particle or clay mineral, so it will arrange itself like the positive hydrogen will be directed toward this negative one. Okay, this will be directed to this negative charge. Okay, so you can see these particles over here. These are the soil molecules, water molecules, and these are surrounding this, and these water molecules are making the you can say the film around these particles, these particles of clay. Okay, so whenever a clay particle is surrounded by these water particles, it will have some plasticity. Already I told you in chapter number 2. Okay, so uh, talking about the forces that are present over here, so there are two types of forces. Number one, you can see it here, that it attracts the negative charge or the positive charge particles towards itself. But as we consider that the soil is completely dry and no water is present over here, so what will be the situation then? Negative charged particle of clay will be in contact or will face a negative charge particle. So negative will repel each other. So the clay particle will keep on repelling each other. Okay, so then how it is cohesive? Then we have another type of force that is being developed over here, that is called van der Waals forces. Okay, van der Waals forces means, or it refers to those forces which are due to the inter like the property of the clay particle or the atoms of the clay particle. Okay, and all the atoms or the elements that are present in these clay particles are like attracted to each other with a specific force due to these electrons and protons arrangement of the particles. Okay, so sometime when the van der Waals forces overcome these negative charge of the clay, okay, so then the clay particle will come close to each other. Okay, sometime it will be like van der Waals forces will be less as compared to these negative charge repulsion of the clay particles. Then the clay particle will move away from each other. Okay, so the situation will be like these clay particle will move in a zigzag motion during the when it is poured in water. Okay, placed in water or in free space. Okay, and that zigzag motion is called Brownian motion. Okay, this is called Brownian motion. Okay, sometime when these clay particles are like having some other materials inside it, and these material are having like flocculation types of properties, and these clay particles are being attracted toward that materials, like for example we have a magnesium of positive charge over there in between the clay particles. So what will happen? The clay particles will surround this magnesium particle. Okay, and will form a flocculate. Okay, so the situation will move from this to this. You can see in this figure. Okay, first of all the particles are dispersed, clay particles are dispersed, no forces between them. When suddenly an extra material like magnesium or positive charge material is placed over here, so what will happen? The clay particle will come close to each other and will form a flocculate. Okay, and this process is called flocculation, and lot of more particles will also come closer, and this will be the situation of the salted flocculation. So you can achieve this flocculation with the help of salt as well. Okay, by putting some salt to the clay. Okay, so this will be like a structure of the cohesive soil. I hope you got the point. Now coming to this next thing, what is domain, cluster and peds in case of the cohesive soil? So simple. Domain are those small particles rearranged and come close to each other. Like for example, you can see it here that these are 2-3 particles that are coming close to each other and are in contact with each other, are having some cohesion with each other. Okay, then these particles combine many domains will group together and will form a cluster, this thing. Okay, then many clusters will group together and will form a ped. Okay, so here you can see this is a ped. Okay, this is made up of clusters, this is a ped made up of clusters. Okay, this is a pairs that is made up of cluster, and again many pairs will combine and form a soil arrangement and like cell size particles and other materials. Okay, so this will be that arrangement of the cohesive soil in a broader view you can see. Okay, now let me clear it first. You can see it here that many domains, as I told you, domains will group together to form a cluster and clusters will group together to form a ped. Okay, then these peds will group together to form that whole sample of the soil clay. Okay, so in between these peds, clusters and domains, you will have an arrangement of silt as well. Some silt particles will also be in between, will be present in between these clusters, and here it is also you can see, and some words here as well. Okay, okay, these domains are actually microscopic, you can't see it with naked eye, and these clusters are sometime again these are microscopic and sometime visible with the help of naked eye or with the help of some light you can see it. Okay, but these beds are almost visible with naked eye as well. Okay, because they are of like greater size. So here it is that clear discussion about this cohesive soil and all the situations. Dispersed structures formed by settling of individual clay particles, more or less parallel orientation. So sometime you can see that these soil particles will settle down in a zigzag motion, as I told you, Brownian motion. Okay, so all that clay particle will be seem like they are dispersed while settling down in the water. Okay, sometimes these clay particles will come close to each other and will form flocculents. Okay, so then they will be called flocculent structures, and domains are actually aggregates or aggregated or flocculated submicroscopic unit of clay particles. Okay, so submicroscopic mean you can see it with the help of microscope clearly that two particles are many particles are in contact with each other and having some attraction with each other. So these are called domains, and then domains group together to form clusters and beds. Already I told you in the previous slide. Okay, so that's all about the structure in cohesive soil and non-cohesive soil, and simple we also discussed a simple formula for that single grain soil as well. So that was like a discussion about structure of the soil. In the next lecture, inshallah, we will discuss the classification of soil. Okay, so you can see in this picture different types of soils are available. Okay, and they have different types of properties. So how to classify different types of soil based upon their properties. Okay, this will be discussed inshallah in the next lecture. I hope you got something new to learn from this lecture. Thank you very much. Assalamu alaikum.